Apple Pencil here. Okay. Chemistry 1411. We ended up somewhere around here last class where we were looking at the relationship between standard cell potential, standard change in free energy, and equilibrium constant. And if you remember, we went through this slide here where we showed that delta G is equal to the negative of the number of electrons transferred in our reaction times the Faraday constant, which is shown here, multiplied by the cell potential. We could say similarly that the standard free energy change is equal to negative N times F times the standard cell potential. But we also know from the thermodynamics chapter that delta G is equal to negative RT times the natural logarithm of our equilibrium constant. And so if we put these two together, since they're both equal to delta G, we can solve for the standard cell potential as being RT over NF times the natural logarithm of K. And I told you, you can simplify it to this here, that the standard cell potential is equal to 0.0257 volts over the number of electrons transferred multiplied by the natural logarithm of K. And I didn't go over the derivation of how to get from here to here. And I told you it's based on the fact that a natural logarithm is the same thing as a log to the base of E. And if you want to take the time to figure that out, you can. And the reason that we put both of these formulas in the slides and why I bring up both of them in class is because if you are the kind of person who peruses the internet and looks for more information on the kind of topics that we study in class, you're going to see both of these formulas. The one that I'm going to use probably 90% of the time or 99% of the time will be the natural logarithm form here of the standard cell potential. But again, we see that now we can draw a relationship between equilibrium constant, standard cell potential, and standard free energy change. If we look at the values for delta G, standard cell potential, and equilibrium constant, you see I have them summarized in this table here. If we have a negative delta G, right, if our delta G is less than 0, we know that we've got a spontaneous reaction. But since delta G is equal to the negative of N times F times the standard cell potential, that means that the E cell, or the standard cell potential, is going to be a positive number. And of course, our K would be greater than 1. The opposite is true when delta G is positive. When delta G is positive, we're dealing with a non-spontaneous reaction. This equation is going to render our standard cell potential as being a negative number. Our equilibrium constant will be less than 1. And when delta G is exactly 0, well, that means that our standard cell potential is also going to be 0, and our K is going to be equal to 1 in that case. All right, and you need to be familiar with all of those. Standard cell potential, we know that most of these galvanic cells that we deal with are set up at 25 degrees Celsius, which is pretty close to room temperature, 298 Kelvin. And usually the standard cell, or not usually, but the standard cell should start out with solutions that are at 1 molar. And of course, we're at a pressure of 1 atmosphere or 1 bar. Well, let's take all of these equations and see if we can work them into a problem. This is an example from our textbook, and it asks us to use the data from Appendix L, which is nothing more than the standard reduction potentials. And of course, I will provide these for you, potentials. I will give these to you on the exam. You don't have to memorize any standard reduction potentials. Maybe the standard hydrogen electrode would be wise to memorize at 0 volts. Anyhow, you're going to use the standard reduction potentials to calculate the standard cell potential, which is E naught cell, standard free energy change, and the equilibrium constant, which of course is, you guys know, is K. And we're going to solve for all 3 of those for this reaction at 25 degrees Celsius. And then we're going to comment on the spontaneity of the forward reaction and the composition of the equilibrium mixture of reactants and products. Well, what's the reaction that's going on here? We have silver that is being reduced. So if this is reduction, right, this is our cathode. And we have iron that is being oxidized. So if this is oxidation, this is our anode. Well, if we look up the standard reduction potentials for silver and iron 2+, we see that for the reduction of silver, which would be 2 silver ions plus 2 electrons, and I'm writing out what's going on in this reaction. If you look in the table, it's just going to say silver plus 1 electron, but since we're starting it with 2 silvers, we're going to use 2 silver ions plus 2 electrons gives us silver, which is a solid. We see that the cell potential, or the standard reduction potential, rather, would be 0.80 volts. If we look up the standard reduction potential for iron, so the reaction that's occurring here is an oxidation, but if we look up the standard reduction potential for Fe2 plus 2 electrons producing iron in the solid phase, we see that the standard reduction potential is negative 0.45. Now, I took these values from the table that I had in the slides that I showed you last lecture. If you look up the values, these standard reduction potentials in our appendix, they might differ slightly, but they won't be enough to affect your answer. You'll still be able to answer the question and get the right answers. Anyhow, how do I calculate the standard cell potential? Standard cell potential is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. This is a formula I would recommend memorizing. So we have our cathode. Which one of these is our cathode? Well, remember, the silver is the cathode because the silver is being reduced. So we have 0.80 volts, subtract the standard reduction potential of our anode, which is the iron being oxidized to iron 2+, so subtract negative 0.45. When you take a negative and you subtract it from something positive, it's like adding it, isn't it? So we have the standard cell potential is being positive 1.25 volts. Since it's positive, that tells us that the reaction is spontaneous in the forward direction, right? Again, we have a positive number here. That means that our delta G, right, our delta G naught is going to end up being a negative number. That means that although this is a reversible process, in the way that it's written here in this equation, it's spontaneous in this direction. All right, well, now that we've calculated the standard cell potential, let's see if we can calculate the standard free energy change. So I'm trying to write small because I don't have a lot of, well, actually I did give myself more space over here, so maybe I'll work over here. So our standard free energy change is going to be equal to negative n, the number of electrons transferred, multiplied by the Faraday constant, multiplied by the standard cell potential. How many electrons are being transferred? Well, if I have 2 silver ions that are being reduced to 2 silver atoms, I'm transferring 2 electrons. If I have iron 2+, right, that's being produced from iron, well, how many electrons are going to be lost during the oxidation process? The answer is 2 electrons, so my n is equal to 2. So I have negative 2 times the Faraday constant. Our book provides the Faraday constant with 5 significant figures. A lot of places you'll see it with just 3. You'll see it listed as 96,500. You can put in all the sig figs if you want, so 96,485 coulombs per mole, multiplied by the standard cell potential, which is 1.25 volts. Remember that 1 volt is equal to 1 joule per coulomb. So we can put that in here, joules per coulomb. Let's see what cancels. We have coulombs canceling, and we're ending up with joules per mole. That's good because delta G is usually listed in kilojoules per mole. We get that our standard free energy change, again, we have a negative because it's a spontaneous reaction written in the direction it's shown. Our delta G is going to be equal to negative 2.41 times 10 to the 5th power joules per mole, which is the same thing as delta G naught is equal to negative 241 kilojoules per mole. And so again, we can write down that the reaction is spontaneous in the direction written. So it's going to be spontaneous in the forward direction. The last thing that we need to calculate is the equilibrium constant. Well, we have a formula that relates our standard cell potential, which was the first thing that we calculated, that relates our standard cell potential, E naught cell, to K, don't we? E naught cell, which is the standard cell potential, is equal to 0.0257 volts divided by N multiplied by the natural logarithm of K. Again, this is a formula that I'm going to provide for you on the exam. If we solve for the ln of K, which is what I'm going to do next, we get that the ln of K is going to be equal to E naught cell divided by 0.0257 volts divided by N, which is the same thing as saying E naught cell multiplied by N divided by 0.0257 volts, like that. So now if we want to solve for K, we can say that K is going to be equal to E to the power of, E naught cell multiplied by N, and in this case is 2, divided by 0.0275 volts. Now let's just plug in some numbers. So we get our E is equal to our E cell, which was 1.25 volts, multiplied by N, which was 2 for our 2 electrons that are transferred, divided by 0.0257 volts. You see that the volts cancel, and I end up with a number that is E is equal to 97.3, or E to the power of 97.3, and I get that my K is equal to 1.8 times 10 to the power of 42. Now, you probably noticed that this is a huge number, okay? This is a gigantic number. 1.8 times 10 to the power of 42. I mean, a mole, for Pete's sake, is 6.02 times 10 to the 23rd power. So this is a really, really big number. I'm trying to find the example on my book, or in the book here. And when you look at the answer in the book, it says that K is equal to 1.3 times 10 to the power of 42. Since I have such a big number here, since the number is just so gigantic, it's not uncommon for them to be off by a little bit, for the mantissa to be off by a little bit, okay? Very uncommon for that to happen. Now, if you're wondering, well, and what if I get 1.8 and the book says it's 1.3, and what if I get it wrong on an exam? Well, trust me, the answers that I put on an exam will be such that if you make a little bit of change in the significant figures and you end up with a difference like this, it will be abundantly clear whether you have the right answer or not, okay? So there's going to be no trick answers when the exponents are, this gigantic to try to mess you up or something like that. Okay, there we go. So this is a really classic question in electrochemistry. I can remember the first time I taught electrochemistry at the junior college that I worked at up in Canada. And one of the most classic questions is a question where you are given a redox reaction. You're asked to calculate E naught cell, or the standard cell potential. You're asked to calculate delta G. From the positive E cell and the negative delta G, we can say that the reaction is spontaneous, the way that it's written. And then from our K value, since the K is so large, we can say that the reaction is mostly products at equilibrium. So we'll say here at equilibrium, we have mostly products because our K is so huge. All right, well, let's switch gears for a second here. And I would say this is switching maybe half a gear, because up to now, we've only looked at standard cell potentials, haven't we? We've looked at standard reduction potentials, but we've always really focused on calculating E naught cell, the standard cell potential. That's when we had gases at a pressure of 1 atmosphere, which again is close enough to 1 bar. All concentrations were 1 molar. Well, you remember when we did the thermodynamics chapter that reaction conditions are going to have an influence on delta G. And so E is also going to be affected by concentration or the conditions of the reaction, right? This isn't standard cell potential. This is just difference in free energy at non-standard conditions. So now we're going to focus our attention on E cell, right? Not standard, right? The not symbol means standard. And since we don't have that symbol here, we mean non-standard. Well, how could we do that relationship? We're going to look at that in a second. But before, I want to talk about how would concentration affect your potential, right? How would concentration affect E in terms of how many volts? Well, voltage is going to increase and the reaction will become more spontaneous. How? When we apply Le Chatelier's principle, right? This is just based off of Le Chatelier's principle, and we spent a lot of time talking about this in class. If the concentration of a reactant is increased, right? If we have A in equilibrium with B, let's say, if we jack up the concentration of A, that's going to drive the reaction to the right. What if we decrease the concentration of a product? That's also going to drive the reaction to the right and cause it to become more spontaneous. In fact, it's one of the main ways that we cause a lot of reactions to give us a lot of product, and that's kind of an unpolished way of saying it, but the point still stands. What else? We can decrease the voltage, or we can cause the reaction to become less spontaneous if we do the exact same or the exact opposite scenarios, right? What if I was to decrease the concentration of the reactant? Well, that's going to push the reaction in this direction. Similarly, if I was to elevate the concentration of the product, then it's going to push the reaction back this way. Again, we're just applying Le Chatelier's principle, and we spent quite a bit of time. I remember one day in class specifically, we went over many examples of this. Okay, now how do we tie all of this to a non-standard cell potential? Let me show you. We're going to have to revive one of our old equations. This equation here, the delta G for a reaction is equal to the standard free energy change plus R times the temperature multiplied by the natural logarithm of Q. And that means you need to know how to calculate Q, but we've calculated K's and Q's enough times that my students are probably pretty rock solid at that. Well, we have two expressions for delta G. We have delta G is equal to negative N times F times E. This is non-standard. This is non-standard. We also have the standard free energy change is equal to negative F times F, negative N times F times the standard cell potential. So now what we're going to do is we're going to take these two expressions right here, and we're going to plug them into this formula right here. And we end up with this guy right here. And then what's going to happen is we're going to divide everything by NF, right? If I divide all these by negative NF, divide by negative NF, divide by negative NF. Oops, what am I doing here? My Apple Pencil's working weird or what? Anyhow, divide by negative NF, and then we divide here by negative NF. What happens? Negative NF cancels here, it cancels here, and we end up with this equation that we call the Nernst equation, named after Nernst. So E for our cell, which is left out, we leave it the subscript cell just to make it simple. So this is a non-standard conditions is equal to E naught cell, and this is at standard conditions. Subtract RT over NF multiplied by the ln of Q. Now, temperature can vary, but let's face it, when we're setting up galvanic cells, we're usually dealing with aqueous solutions at around 25 degrees Celsius. So since T doesn't vary a whole hell of a lot, we can simplify the Nernst equation to this form right here. This is the one I'm going to use most of the time. Okay, E is equal to the standard cell potential, subtract 0.0257 volts divided by the number of electrons transferred, multiplied by the ln of Q. If you want to derive the one that's on the bottom right here, the logarithm form, you can do that. Again, I told you last class that a natural logarithm, right, a natural log is the same, sorry, the natural log of x is equal to the log base e of x. So you can solve for this one if you want, but don't worry about it. I would never ask you to do that in 100 years. Well, let's face it, maybe in 100 years. But in 100 years, I won't be here. So let's move on from there, and let's see if we can solve a problem where we're dealing with a galvanic cell that is not at standard condition. So it says predict whether, or sorry, I shouldn't say a galvanic cell. Predict whether a redox reaction is going to be spontaneous at non-standard conditions. So all it's asking is, it says, predict whether the reaction is going to proceed spontaneously the way it's written. So, is it going to be spontaneous in this direction? Given that the concentration of the cobalt ions are 0.15 molar and the concentration of the iron 2 plus ions are 0.68 molar. Well, there's nobody here that can't calculate a Q, right? We've calculated so many Qs throughout this course. And the formula that we're going to use to solve this is that E of our cell is going to be equal to the standard cell potential, subtract 0.0257 volts divided by the number of electrons transferred multiplied by the ln of Q. Well, the first thing we're going to do is we're going to solve for the standard cell potential for this redox reaction. I have the cobalt that's being oxidized to cobalt 2 plus. So this is oxidation. This is my anode. I have iron 2 that's being reduced to iron. This is reduction. So this is my cathode. If I look up the standard reduction potentials for these two reactions, I'll start with the cobalt. Cobalt 2 plus 2 electrons gives you solid cobalt. The standard reduction potential is negative 0.28 volts, negative 0.28 volts. The standard reduction potential of iron 2 plus 2 electrons to give you solid iron. Its standard reduction potential is negative, sorry, I can't read, I need new glasses, negative 0.44 volts. So my E naught for my cell is going to be equal to the standard reduction potential of the cathode, subtract the standard reduction potential of the anode. I get that my E naught cell is going to be equal to negative 0.44 volts, subtract negative 0.28 volts. So I get that my E naught cell is going to be equal to negative 0.16 volts. There we go. That's my standard cell potential. Now I have this number, and I can solve for Q pretty easily, can't I? Right, because I know that Q for this reaction is going to be equal to the concentration of the cobalt ions divided by the concentration of the iron 2 plus ions. Remember, we only include things that are in aqueous solution or that are gases, the pressure if they're gases. We don't include pure solids and pure liquids. So now I have everything to solve for my E at non-standard conditions, which is what I'm dealing with in this question. So I have, well, you're going to have to follow along with me here. I have the E is going to be equal to E naught of my cell, subtract 0.0257 volts, divided by N times the ln of Q. I start plugging in some numbers. I get that my E is equal to negative 0.16 volts, subtract 0.0257 volts, divided by N. Right, I'm transferring 2 electrons, so N is equal to 2. So I'm going to plug in, oops, I didn't mean to do that. There we go. I'll plug in 2 in my denominator, multiplied by the ln of, and since Q is equal to the concentration of cobalt ions over the concentration of iron 2 plus ions, it's going to be the ln of 0.15 divided by 0.68, like that. Okay, let's get to it. We have the E is equal to negative 0.16 volts, subtract 0.0129 volts multiplied by negative 1.51. I'm just simplifying here. We get that E is equal to negative 0.16 volts, subtract negative 0.019 volts, and then we get that the E of our cell at non-standard conditions is equal to negative 0.14 volts. So even though we're at non-standard conditions, I can say that the reaction is not spontaneous as written. Reaction is not spontaneous as written since E cell is negative. Right? In order for the reaction to be spontaneous, E cell would have to be positive. Let's try another example where we end up solving for the concentration of an ion. It says a galvanic cell is constructed from a silver half cell and a copper half cell. The copper half cell contains 0.1 molar copper-2 nitrate, and the concentration of the silver ions in the other half cell is unknown. If the silver electrode is the cathode, so they kind of spell it out here for us, don't they? They tell you that the silver electrode is the cathode, and they give you the non-standard cell potential is 0.1 volts at 298 Kelvin. What is the silver ion concentration? Well, if the silver electrode is the cathode, right, the silver electrode is where the reduction is occurring. And so that means that the copper, this copper electrode, or the solid copper, is getting oxidized. So we have solid copper plus silver ions, which is going to produce copper 2+ ions plus silver. Remember, the metals are in the solid phase, the ions are aqueous, and the only thing I need to do here is to balance this out in terms of my charge. So if I have 2 positives over here, it gives me 2+ on that side, and now I'm balanced. So this is my redox reaction in question. All right, if you're, again, curious about how I came up with this, look, the copper is undergoing oxidation. Therefore, this is the anode. The silver is undergoing reduction. So this is my cathode, like that. I'm going to skip the whole thing about writing down the standard reduction potentials for the copper ions and for the silver ions. I'm going to skip that step of going through the table. I've already gone ahead and looked them up. So the standard cell potential, which is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode, is equal to 0.80 volts subtract 0.34 volts. So I end up with a standard cell potential that is equal to positive 0.46 volts. That is my standard cell potential. Now I have everything that I need to plug into my equation. E is equal to E naught minus 0.0257 volts divided by N multiplied by the ln of Q. Because Q is going to be equal to the concentration of the copper 2+ ions divided by the concentration of the silver ions to the power of 2, right? Because I have a stoichiometric coefficient of 2. So Q is going to be equal to 0.10 divided by x squared is the way I'm going to put it. So X will be the concentration of my silver. Remember that copper 2 nitrate is completely ionic. For every 1 formula unit of copper 2 nitrate, I'm going to end up with 1 copper 2+ ion. Give me a thumbs up if you're with me so far. And if you have a question, feel free to stop me at any point. All I'm really doing here is figuring out what the Q is. Now I've got that. I know that N is going to be equal to 2 because I have 2 positives over here and I have 2 positives over here. Okay, does anybody besides Joey follow along? Because this is important. We're going to have an exam on this pretty soon. So stop me if there's a part you don't understand. Feel free. Mr. Dion will not be offended in any way. So I want to calculate the concentration of my silver ions. I know what the non-standard cell potential is. It's 0.10 volts. It's going to be equal to 0.46 volts, subtract 0.0257 volts, divided by 2, since my n is equal to 2, multiplied by the ln of 0.10 divided by x squared. Now I just need to simplify this. So what do I do? So let's do it. Did I give myself more space? I did. Nice. So I'm going to get back to work over here. And why don't I simplify a little bit more here? And we'll say that 0.10 volts is equal to 0.46 volts. Subtract 0.01285 volts. I know I'm carrying an extra sig fig here, whatever. It's the land of the free for now. Times the ln of 0.10 divided by x squared. Okay, so now I'm going to take this and I'm going to simplify it even more. So I'm going to copy it. Now it's just a matter of doing a little bit of algebra, isn't it? I mean, this doesn't intimidate you guys, I'm sure. Come on. What happened? Copy. There we go. Okay, we got that. So now I'm going to rearrange the formula more. So I end up with 0.01285 volts multiplied by the ln of 0.10 over x squared is being equal to 0.36 volts. So I just added this to this side, and then I subtracted this from the 0.46 volts is all I did. Then I'm going to divide everything by 0.01285, and I get that the ln of 0.10 over x squared is equal to 28.0. Then I get that 0.10 over x squared is equal to e to the power of 28.0. And e to the power of 28.0, I got 1.47 times 10 to the power of 12. And so then we can say that x, we'll go from here and we'll say that x is going to be equal to the square root of 0.10 divided by 1.47 times 10 to the power of 12. When you punch all that spinach in your calculator, you get the x, which is the concentration of a silver ion, is equal to 2.6 times 10 to the negative 7 molar. Okay, just a little bit of algebra there. I know I went over it pretty steppy for some of you. You're probably like, just get on with it, Mr. Dion. Okay, I could have done this faster than you, but whatever. You know, sometimes it's nice to stop and do a little bit slower. Give me a thumbs up if you think you could do that one. All we're doing is using this equation, and we have everything except for the concentration of one of the ions, which produces our Q. So just a little bit of math there, just a little bit of algebra. And remember, when you sign up for this class, you've got to have a certain amount of algebra skills. The good news is that when you take, what I always think is like one of the best things in terms of the math of general chemistry too. I know that some students find it challenging, but the bottom line is that you don't need calculus. I know that a lot of you are either taking calculus or have taken it already. You don't need to do differential equations or do integrals for this class, which lowers the complexity compared to something like quantum mechanics. Anyhow, I'm just going to cover the concept of a concentration cell with you quickly here. So a concentration cell is constructed by connecting two nearly identical half cells. Each half cell is going to be based on the same half reaction and using the same electrode. The only thing that we vary is the concentration of one of the redox species. So the potential of a concentration cell is therefore determined only by the difference in the concentration of the chosen redox species. So if we look at this galvanic cell that's shown here, you see that we have zinc and zinc 2 plus on the side of our anode, and we have it also on the side of our cathode, right? So if you write out the oxidation reaction and the reduction, half reaction. What happens when we tally those up? You see that the electrons cancel, and we end up with this as being our overall reaction, that we have zinc 2 plus at a concentration of 1 molar produces zinc 2 plus at a concentration of 0.1 molar. If we use the equation that I have in the yellow box here, if we use that equation, you can see that Q is going to be equal to the concentration of the dilute zinc ions divided by the more concentrated zinc ions. So we have 0.1 divided by 1. And so the driving force for this reaction, and when you do the calculation, you see that the standard cell potential is going to be 0, right? Because the cathode and anode are both identical. And so their standard reduction potentials are going to be the same. So we lose that. That becomes a 0. And then we just take the ln of the concentrations, right? The ln of the concentration of the zinc 2 that's dilute divided by the concentration of the zinc 2 that's more concentrated. And look what we get for an E. It's positive. Okay, it is spontaneous. This reaction is spontaneous the way it's written. Does that make sense? Absolutely it does. Based off of Le Chatelier's principle, we have more concentrated solution, which should be going to a more dilute solution. That totally makes sense, right? If we increase the concentration of the reactants, it's going to push the reaction to the right. If we decrease the concentration of the products, it's going to push the reaction to the right. So it makes sense that it's a spontaneous reaction. However, when you do these kinds of problems, what you'll see is that the cell potential is usually small, okay? It's usually not a very big one. All right, so we have a really small cell potential, which is 0.0296 volts in this case. So that's a concentration cell. Might be worth the value of maybe one question on your next exam, exam 4. Okay, I told you in the interest of time, we're going to skip section 17.5. So we're going to skip that. I'm not going to ask you any questions about batteries. And you can read all about lithium-ion batteries and lead batteries in this section. Talks about fuel cells. This next section deals with corrosion. We're also going to skip that. It talks about the formation of rust and, you know, all that kind of stuff. We're going to skip right to the last section, which is 17.7, which deals with electrolysis. So electrolysis, so far we've looked at spontaneous redox reactions, haven't we? Yeah, that's all we've talked about. We're spontaneous redox reactions. But electrolysis is the process in which electrical energy is used to cause a non-spontaneous chemical reaction, and we're talking about redox reactions, to occur. The example that's shown here is the electrolysis of molten sodium chloride. So this is sodium chloride in the liquid phase. You heat it up and you melt it. And what you can do is when you take liquid sodium chloride, so what do we have in solution? We've got sodium ions in the liquid phase, and we've got chloride ions in the liquid phase. What are we going to do to those ions? Since this is electrolysis, we're talking about a non-spontaneous process. We're going to cause the oxidation of the chloride ion, right? Oxidation occurs at the anode. And we're going to cause reduction of the sodium ions, and that occurs at a cathode. If you look at these reactions here, the way that they're written going forward like this, it should be no surprise, or it should come as no surprise to you that both of these are going to require energy from a battery, aren't they? They're going to require that electrical energy, that boost, because both of these processes written the way they are super non-spontaneous, aren't they? They're very non-spontaneous processes. In fact, if you calculate the standard cell potential here, right, if we use, I'll just erase this here. If you use the formula that the standard cell potential is equal to the standard reduction potential of the cathode, subtract the standard reduction potential of the anode, well, the standard reduction potential of our chlorine is going to be negative 2.71 volts. And then we're going to subtract for our anode positive 1.36 volts. And we're going to end up with a standard cell potential for this cell as being negative 4.07 volts. That, my friends, is a very non-spontaneous process. That is why we have to have that external supply of energy from our battery in order to cause the reduction of sodium to produce liquid sodium and the oxidation of chlorine to form chlorine gas. So the electrolysis of molten sodium chloride or sodium chloride in the liquid phase is in fact I think it's the major process that's used for producing pure sodium and pure chlorine gas. Again, in order for this reaction to become spontaneous, in order to get this process to occur, we have to apply a battery. Oops. We have to apply a battery. And not only that, but the positive potential of the battery has to be greater than the negative potential of the cell. And so the voltage of the battery is going to have to be greater than 4.07 volts. All right, well, that's enough about that. This is a picture of what's called a Downs cell. And Mr. Dion is not the world's renowned expert on Downs cells, but a Downs cell is, again, a cell that's used to affect the electrolysis of molten sodium chloride. And the way that it works is that since liquefied sodium, sodium that's produced in the liquid phase, because that's what you produce at the cathode, is less dense than the liquefied sodium chloride. So I think it floats up to the surface, or there's a way that they get it to flow out through pipes or something. And then for the chlorine gas, we can imagine, of course, since that's a gas, they have ways of harnessing the gas over the top of the reaction. So kind of an interesting concept, the Downs cell, which again is just nothing more than the electrolysis of molten sodium chloride. In fact, last night I was just sitting around and I went on YouTube and tried to find some videos of people doing the electrolysis of sodium chloride, and I stumbled upon a video of somebody affecting the electrolysis of sodium hydroxide, and I thought it was actually pretty cool because you could see the oxygen bubbling off and you could see them actually collect the sodium. And they took the sodium that they collected and they actually took it outside and threw water on it, and poof, of course it burst into flames. So I thought that was pretty interesting. Anyhow, let's move on from there and let's talk about the electrolysis of water. This is a figure that comes directly from your textbook. And I mentioned this a couple times to you throughout the semester that I went to high school with a couple of cats who tried to do the electrolysis of water, because when you perform electrolysis on water, what happens is at the anode, you have an oxidation reaction occurring, right? Remember anox and red cat? What you're doing is you're oxidizing the oxygen from a -2 oxidation state to a 0 oxidation state. And the standard reduction potential of the water to produce oxygen is positive 1.23 volts approximately. But what happens at the cathode is the reduction reaction. And what you're actually reducing is not water, you're actually reducing hydrogen. And if you're wondering, why would you be reducing a hydrogen ion? Because in water, Mr. Dion, I thought you told me way back in the acids and bases chapter that because of Kw, the concentration of H plus in water is only 1 × 10⁻⁷ molar. Well, hold the phone, because what we actually have in here is not just water. We also have water plus a strong acid. Okay, it says water can be electrolytically decomposed, or we can perform electrolysis on water. To improve the electrical conductivity without putting in different redox species, we put acid in there to increase the hydrogen ion concentration. So what you're doing is you're reducing H plus ions or protons, right? Because we're going from an oxidation state of +1, oops, didn't want to use the highlighter, of +1 to 0. But what happens when we tally up these two reactions? When we tally up these two reactions, we'd have to multiply this reaction by 2 first, but we end up canceling the 4 electrons and we end up canceling the 4 protons. And here's the overall process. Okay, that we take water and we convert it into hydrogen gas and oxygen gas. Notice that there's twice as many moles of hydrogen gas as there is oxygen gas. So the volume of the hydrogen gas should be twice as much as the volume of the oxygen gas. Also notice that the standard cell potential is negative. It's negative 1.229 or negative 1.23. So that tells us this is a non-spontaneous process, and that is why we have to provide a battery in order to get this reaction to move forward. And of course, the voltage of that battery would have to be greater than 1.23 volts. Well, the last section deals with the concept of electrolysis and mass changes. So now we're going to get into a little bit of stoichiometry. It won't take us long, and we'll take a look at a problem or two that involves amperes in relating that to charge and mass changes in reactions. But before we do that, I want to cover electroplating. I don't know if you guys have ever heard of electroplating before. I'm sure that somebody who's in class has heard of electroplating before, but electroplating is basically where we take, a cheap metal, like maybe some kind of steel or iron or something, and then we coat it with a more expensive metal. So here they're showing the electroplating of a spoon that's going on. So when you buy, stainless, silverware or silver, you get it the silverware at maybe, Christmas and Thanksgiving or whatever holidays you celebrate. The way that the silverware is produced is by the process called electroplating. So if you just follow along with me here, it says electroplating does nothing more than puts a thin coat of a metal on top of some kind of conducting surface. And so this is, used to just make a more attractive finish or something that's more resilient maybe. Common metals that are used are chromium, right? If you've ever seen a chrome bumper, it's just the chromium is on the top. It's made by electroplating, gold, nickel, silver, tin, etc. So what happens when or during the process of electroplating? So what's happening here is that the anode consists of a silver electrode that's shown on the left, and then the cathode is on the right. And it's a spoon, which is made of some kind of inexpensive metal. Both of the electrodes, both the anode and the cathode, are submerged in a solution of silver nitrate, and then a sufficient potential is applied that results in the oxidation of the silver anode. So the silver anode decomposes, and we produce silver ions. And then we get reduction of the silver ion occurring at the cathode, which is the silver spoon. Right, so the silver ions get combined with electrons from our source, and we end up making or putting solid silver on the spoon like that. So the net result is the transfer of silver metal from the anode to the cathode. All right, so really all we're doing is taking silver from here and putting it on the spoon, but we're using the process of electroplating. So with that in mind, how does all this stuff kind of relate to mass changes? Well, this is a little figure that shows dimensional analysis, and I took this from another textbook, and it shows you how you can relate current and time to charge in coulombs, and then you can relate that to number of electrons, you can relate that to moles of a substance, and of course, if you know the number of moles of a substance, well, then you can determine the mass of a substance. But before we do that, you have to know that 1 ampere is equal to 1 coulomb per second. I have it written here, the charge in coulombs is equal to amperes times seconds, but I find it more convenient to think of 1 ampere as being 1 coulomb per second. So we can see the relationship between current and time. Next, it says charge in coulombs. Well, we know that 1 mole of electrons has a charge of 96,500 coulombs, right? That's the Faraday constant. This is F. So F is equal to 96,500 coulombs per 1 mole of electrons. Now, it gets a little simpler. You guys remember that if we have the number of moles of electrons, we can figure out the number of moles of a substance, right? And then if we have the number of moles of a substance, we can figure out the mass of that substance just by using molar mass. Well, with that in mind, let's try taking a look at a problem where we have to explore electrolysis and we look at mass changes. And I actually put an extra problem in here kind of at the last minute, question number 11. So this was supposed to be, yeah, this is example 17.9 from our textbook. Do we need to memorize the metals commonly used in electroplating? I don't know. Joel, how hard is it to remember? You know, you've heard of silverware, right? You've seen a chrome bumper. There you go. There's two of them for you. Okay? So I want you to know those two. Just Joel, though. Everybody else, you don't have to know anything. I'm teasing you, Joel. Yeah. Just have an idea, Joel. Have an idea. I'm giving you a hard time. Okay, let's try a problem. So this one's kind of good because it takes you right back to stoichiometry and a little bit of your old friend, dimensional analysis. I know you missed it. It's been away for a while, but we're going to apply some dimensional analysis. And you know what? If you looked at this slide and you're like, how the heck am I going to connect these concepts to the change in mass or a mass of something? Let me show you how. And once you see it done, it usually becomes abundantly clear to my students how to solve a problem like this. So question is this. It says in one process that's used for electroplating silver, a current of 10.3 amperes was passed through an electrolytic cell for exactly 1 hour. How many moles of electrons went through the cell? And what was the mass of silver that was deposited at the cathode from the silver nitrate solution? So you can see that it's exactly this scenario right here. So this is the same kind of, this is the scenario that we're seeing in example 17.9. Anyhow, so let's see if we can figure it out. Well, if I've got 10.3 amperes, remember I told you that 10.3 amperes is the same thing as 10. Did I say 10.3 when I meant 10.23? Yeah. You ever have arguments with your friends or argument with a family member where you say, I said this, and then the family member says, no, that's not what you said. You said something else, right? And what you heard in your mind was one thing, but what actually came out of your lips was another thing. Well, I feel like the longer lectures go on, the more that I do that thing where I feel like I'm saying one thing to you guys, but then I know something else is coming out of my mouth. So I have to be cognizant of that. Anyhow, kind of a comment on the human psyche there. Anyhow, so I have 10.23 coulombs per second. Well, how many seconds? Does anybody know how many seconds are in an hour? Can anybody just tell me without very much thought? You guys know how many feet are in a mile? How many seconds are in an hour? Thanks, Camden. Thanks, Brogan. Yeah. Thanks, Joey. 60 times 60, right? It's 3,600, Violet, I promise. 60 times 60. Right? You have 6 times 6, which is 36. You have 2 zeros, so 3,600. There you go. So in 1 hour, it's 3,600 seconds. And I just wanted to get that out of you guys just to be a little bit quicker here. So anyhow, let's see here. We got 3,600 seconds in 1 hour. If I was to stop right here, look, my seconds cancel out. I have the number of coulombs that passed in an hour, but it's asking me how many moles of electrons passed in an hour. And I know from Faraday's constant that in 1 mole of electrons, or for 1 mole of electrons, I should say, I have 96,500 coulombs. So you see that coulombs cancel, and I end up with the number of electrons that passed in that 10.3 amps of current over 1 hour. And I end up with a number that is 0. How many sig figs should I have? Who could tell me? How many sig figs should there be in my answer here? The number of moles of electrons. Yeah, thanks, Jamil. It's 4. You know what? We don't do a whole lot of questions where we work with 4 sig figs, do we? But remember, this number has 4 sig figs. 4 sig figs. But 1 hour is an exact number. So we should have 4 sig figs. So we have 0.3816 moles of electrons that passed in the 1 hour. So that's the answer to the first part of the problem. Next, we have what's going on next. It says, what mass of silver was deposited at the cathode from silver nitrate? Well, remember, maybe I should have said this earlier, but I'm saying it now. What's happening here is that silver ions are being reduced by one electron at a time to produce solid silver, right? And the mass of silver is 107.87 grams per mole. We're going to need that in a little bit. So again, I'm only transferring one electron, right? I'm moving one electron for every silver atom. Okay, so that means that if I have this many moles of electrons, 0.3816 moles of electrons, and I know that for every 1 mole of electrons, I produce 1 mole of solid silver. And I know that in 1 mole of solid silver, I have 107.87 grams of silver. Look at this. Moles of electrons cancel, moles of silver cancel, and we end up with 41.18 grams of silver. So that is how much silver was deposited at the cathode during this electroplating process. Once I was looking at the slide or my slides the other day, I kind of decided that this isn't enough practice on this whole concept of using electrolysis to produce a change in mass. And so last night, so if you don't have the latest edition of the slides, I slapped on one problem at the end. And this problem, I was, I'm always looking for a good source of problems for my students. And so I went directly to the ACS study guide and said, what kind of, I wanted to know the level of problem that they would ask my students. What kind of level did they expect from the ACS? And this question comes directly from the ACS study guide. So it says, how many minutes are required to plate 2.08 grams of copper when you have a current flow of 1.26 amperes? Remember that 1.26 amperes represents 1.26 coulombs per second. I apologize, you guys. Wednesday, my daughter has a late start to school. I know it's really loud in here. Can you guys hear the noise? Okay, because my daughter's friend comes over on Wednesday mornings because her parents can't drop her off, so she stays over here on Wednesday mornings. And you can imagine what it's like when you get two 6-year-old girls together, combined with my 3-year-old son. So I apologize if it's loud in the background. Anyhow, where was I? Yeah, okay, so I got 2.08 grams of copper. That's what I'm starting out with. And I want to know how many minutes it's going to take. Well, I know that in 2.08 grams of copper, how many moles of copper do I have? I go to the periodic table. I see that 1 mole of copper has a mass of 63.55 grams, so 1 mole of copper. What's the process that's happening here? If I have copper 2, right, that's the process. It's telling me right here, it's copper 2 plus 2 electrons. That means that for every 1 mole of copper that I produce, I need 2 moles of electrons to do it, don't I? Right, look, 2 moles of electrons to make 1 mole of copper. Okay. If I was to stop here, grams of copper cancel, moles of copper cancel, and I would have moles of electrons. Let me relate that to charge now. Because I know that in 1 mole of electrons, or 1 mole of electrons, has a charge of 96,500 coulombs. I know I could keep going with the dimensional analysis here and just solve the whole thing in one fell swoop, but I'm going to break it up into a couple of spots here. So I've got 6.32 times 10 to the power of 3 coulombs. So that's how much current I need, or sorry, not current. That's how much charge I need in order to plate the 2.08 grams of copper. Well, if I know the amount of charge required and I know the number of amperes of current that I have flowing, all I have to do is to solve for time. I'm just going to take my 6.32 times 10 to the power of 3 coulombs. I've got 1.26 coulombs for every 1 second. It's asking me for minutes, so I know that in 60 seconds, I have 1 minute, like that. Coulombs cancel, seconds cancel, and I end up with the number of minutes, which I can't even read my own writing, but it's 83. Oops. It's 83.6 minutes, like that. Again, if you look at the solution that I have posted in the solution slides, you'll see that I did this all in one thing. So basically, I took this part, these last two sections here, right, and I just tacked them on at the end, okay, and then just did the whole thing in one fell swoop. You know what? I've taught this class long enough to know that some students do it that way, and I like to do it that way most of the time, but I know that a lot of students like to break up dimensional analysis just because it kind of helps with the rationale sometimes. And I think that this is in a case where that would be, applicable. To me, it kind of, that's the way my brain thinks about it. I think about the total amount of charge, and then if I know what the amperage is, well, I can figure out the time very quickly. Okay, so that's the relationship between electrolysis and mass changes. And Joel, that covers a little bit about electroplating. And now you know how chrome bumpers are made, or silverware. Maybe you could buy some. I had a friend in Ontario who was buying silverware at a factory where they were making it. He would go into the factory store and he was buying the factory seconds, and then he was selling them on eBay and making all kinds of scratch doing that. So there you go. There's a side hustle for you.